Hi, and welcome back. In this chapter, we're going to be covering Chapter 7 from the CISSP study guide on public key infrastructure, PKI, including asymmetric cryptography, and cryptographic applications. If you're following along in our study guide with our lessons, we are in Unit 2, covering cryptography, and we will finish out Unit 2 with incident response and investigation. Let's get started. If you followed through with Chapter 6 from our last lecture, you understand a little bit about asymmetric cryptography. Asymmetric cryptography creates two keys that will both be a public and a private key. If you encrypt something with the public key, only the private key can decrypt it. And if you encrypt something with the private key, only the public key can decrypt it. This allows us to use asymmetric cryptography, understanding two different keys rather than symmetric, which only had a single key. The benefit of asymmetric cryptography is that it does not require the sharing of your private keys. So I can keep my private key private and you can keep your private key private, but we can still use asymmetric cryptography by sharing our public keys with each other. One of the more common or well-known algorithms for asymmetric cryptography is RSA, named after the creators of Ronald Rivest, Adid Shamir, and Leonard Adleman. RSA is a public key asymmetric cryptography algorithm. The algorithm follows with the basic mathematical concepts of prime numbers are very difficult to factor. Using the factorization of prime numbers as the difficulty part in asymmetric cryptography, we are able to use this algorithm. The algorithm goes as such. Choose two large prime numbers, P and Q. Large being large numbers, not 10 or 15 or 20, but something very, very large. Many, many digits. Create N that is the product of those two numbers. Select an E such that E is less than N and is relatively prime to P minus 1 and Q minus 1. There are no common factors between the two. Then find a number D such that E multiplied by D is equal to 1 mod of P minus 1, Q minus 1's product. We can now distribute E and N as public keys, keeping D as the private key, and we can create our asymmetric cryptography with these options. So RSA is one of the more common, most well-known asymmetric cryptography algorithms. It's okay if you don't really understand all of the mathematical computations involved in it, simply knowing that we are using the factorization of prime numbers difficulty as part of our cryptography algorithm. It's also really important to understand key length. With asymmetric cryptography, because of the asymmetric nature, we need to have a key length that is much larger than a symmetric cryptography key length. So if you are doing symmetric cryptography and you are having a shared private key, you can have a smaller 128-bit key length. Whereas with asymmetric, you're talking about very large key lengths, up around 3,000 bits. The elliptical curve, which we'll discuss in just a minute, takes advantage of the difficulty in solving logarithmic problems, which we'll get into in the next slide. Understanding with the key length that with cloud computing, brute force is becoming much more possible. So you want to always be aware of that key length and the complexity of your algorithm. The next algorithm we're going to discuss is the Elgamal algorithm. As you learned about DiffieHellman, which we will describe again in detail in the next slide, we used large integers and modular arithmetic to be able to have the secure exchange of keys. Elgamal took the concepts of DiffieHellman and used it to create the entire public key encrypto system that he used. At the time, RSA was still patented, and therefore the big benefit of Elgamal is that it was released in public domain. There was no patent. Since then, RSA has been released in the public domain, so therefore that significant benefit is no longer applies. A disadvantage of this algorithm was simply that it doubled the size of the message. By using the algorithm, you ended up with twice the size of a message. If the message was small, that wasn't too big of a problem, but if it was a larger message, it would become incompatible to be able to use that large of a message and therefore using that algorithm. The elliptical curve algorithm uses the mathematical properties of logarithms to be able to create this elliptical curve algorithm using elliptic curve cryptography, ECC. So if you ever see elliptic curve cryptography. The algorithm for an elliptic curve from mathematics is simply y squared equals x cubed plus ax plus b, where a and b are both real numbers. If you can find 2 points on the curve, P and Q, and add them together, you can use that piece of information to be able to create an algorithm for cryptography. Even if P and Q are individually known, it's still very, very difficult to find the value of X at any point. So we use the difficulty of being able to find values in logarithms, which is harder to solve in some cases than the prime numbers issue, factorization of prime numbers versus discrete logarithms. Both are mathematical concepts. No, you are not expected to be a mathematical major, simply understanding that the concepts of prime numbers, so a number that is only divisible by itself in 1, and the powers of logarithms are the two underlying mathematical concepts behind these cryptography algorithms. At this point, we're going to get a little more into detail on the DiffieHellman Key Exchange. The point of DiffieHellman is to be able to allow two people to exchange a secret key for the purpose of symmetric cryptography over an insecure channel. We need to be able to have two people, in this example, Richard and Sue, figure out what their symmetric key is. And remember, the biggest problem we had with symmetric key and cryptography was that key exchange, the ability to pass back and forth that symmetric key. How are we going to do that, especially over an insecure channel? We can't obviously just say, here's my key, because anybody listening on that channel can hear your key and therefore use it. So the DiffieHellman Key Exchange uses prime numbers, similar to RSA, to be able to create a secret key using the powers that occur in prime numbers and modular arithmetic. So the algorithm goes like this. Richard and Sue both agree, fine to do this over insecure channels, on two large numbers, P, which is a prime number, and G, which is any integer. Given an integer and the prime number, Richard is going to create a large random number integer, R, lowercase r, and perform the calculation to create capital R, which is simply G to the power of R, and then modular by P, whatever P happens to be. We're going to get capital R from this. Sue, at the exact same time, at home, in her own location, not over the internet, is going to also choose a different random number integer, lowercase s, and perform the same calculation, G to the power of S mod P, to come up with capital S. Capital S and lowercase s are not the same letter. The same number, excuse me. Capital R and lowercase r are not the same number. So really important to understand that. Once we have capital R and lowercase r, or capital R and capital S, Richard and Sue are going to exchange those over an insecure channel. It's okay if somebody else hears this. This is not the problem because that is not used to make the key. What we do is Richard is going to take Sue's capital S and take it to the power of his lowercase r that he has never said over the internet and mod that by P, and he's going to end up with K. The great thing about powers and modular arithmetic and the different things we can do with prime numbers is Sue at the same time can take her capital R that Richard sent her and take it to the power of her lowercase s, mod it by P, and end up with exactly the same key, K, which is our secret key that we now share. By doing this, you are able to create a secret key K without passing it directly over the internet. What is passed back and forth is P, G, capital S, and capital R, but none of those are enough to be able to create K in and of itself. That's the power of the prime numbers. TLS uses DiffieHellman Key Exchange to create a shared key to be able to create a symmetric tunnel so that information can be shared. The point of this is to be able to understand, even if you're struggling with visualizing how that key exchange occurs, the point is that key, K, is never passed back and forth over the insecure channel. We are able to calculate it using the powers of prime numbers and modular arithmetic. Quantum cryptography uses the theory of quantum computing and quantum mechanics. At this point in time, we do not have a practical implementation of quantum cryptography or quantum computing. The concept simply being that we can replace the binary of ones and zeros with multi-dimensional qubits that can be created and evaluated in kind of this flux. We haven't done it yet. However, we are trying, which means if it works, if we can find a practical implementation of qubits of quantum computing, it would be very easy to solve the logarithmic problems of elliptical curves or the prime numbering factoring of RSA and DiffieHellman, which means you always want to be aware of the fact that there may be a time limit on security. Just because we're using RSA today doesn't mean that RSA will always be secure in the future. Keep an eye on your data and make sure that your currently secured data will still be secure in the future based on whatever happens to happen with quantum cryptography and or simply advances in computing power. As we mentioned before, cloud computing has allowed you to do parallel processing and parallel computing to be able to do brute force attacks on cryptography in ways that we were never able to do before. You always want to stay above and beyond where you think you are today, because you never know where we're going to go with cryptography tomorrow. A little later on, we are going to be discussing message digest and digital signatures, but to understand those, we need to explain hash functions. For those of you that are comfortable with hash functions, this will be a piece of cake. You'll understand it just fine. Hash functions allow you to take a long, very large message and to create a unique output value from the contents of the message. We're using concepts like modular arithmetic and random numbers to be able to hash a value of perhaps a file or a message into what can be used as a digital signature. Any change in the file over time will result in a different digital signature. So we can use hashing to be able to take a file, take a message, and be able to create a unique output which can be used to verify or validate that data. The messages must be exactly the same for that hash function to give you the same digital signature. Small differences like spaces or punctuation or even a difference in letters is going to make a significant difference in the hash result. The great thing about hashing functions, because it uses modular arithmetic, it cannot be reversed. It cannot be de-hashed. A couple of common types of hash functions include SHA, MD5, RIPE-MD, and HMAC. The thing about hash functions, the input can be any length, but the output is going to be a fixed length. We are going to say exactly how big we want that output to be. They are extremely easy to compute, especially with calculations and computers. It is always a one-way function, and the biggest point about hash functions is that they should be what we call collision resistant. They should avoid the chance of two completely different files producing the same digital signature. That would defeat the purpose. So we want to make sure that we are collision resistant, one-way function, any input with a fixed output, and very easy to compute. Let's discuss a couple of hash functions now. So listed on your screen are three of the common hash functions. Secure Hash Algorithm, or SHA, has three versions currently. So SHA-1 has been deprecated. It's not useful anymore. The SHA-2 is currently the standard, and SHA-3 has been introduced in 2015. It's a little slower than SHA-2, but it may gain steam as time goes on. With SHA-2 standards, there are 4 different versions, and you really do want to memorize the bit length and the block length for these different SHA hash algorithms. So our 256 uses a 256 bit. In fact, all 4 of these SHAs tell you how many bits they are in how many in the naming. So SHA-256 creates a 256 message digest, and it uses 512 sized bit blocks. 224 uses a 224 message digest with 512, and then our 2 larger ones, so the 2 that are under 200 or 200 or less, are both using 512 bits, and then our 512 and our 384 use 1000 bits or 1024 bit blocks. We always do powers of 2. So power of 2 is 512, powers of 2 is 1024. So 2 to the 9th and 2 to the 10th. So our SHA hash functions will create either a 256, 224, 512, or 384 message digest and that is the size. Remember, the output size is always the same. Input size is anything you want it to be. Our MD5 hash was actually created by Ron Rivest of our RSA fame. He originally had created MD2, which was for 8-bit processors way back when. In 1991, he created MD5, which is still used, but it is subject to collisions. So MD5 hashes create a 128-bit message block or message digest using 512 blocks. So similar to SHA 256, but it's a 128-bit instead of a 256-bit. But MD5 must be 64 bits less than the multiple of 512 because we're going to use those 64 bits for parity. The problem with MD5 is that it is subject to collisions. You can create a secondary MD5 hash, and it happens a little more frequently than they would like. It's still used, but most people would prefer to use SHA-2 over MD5 these days, especially if it's something that's really important to keep straight. The RIPE-MD message digest is an alternative to the SHA, and it's the one that's currently used in Bitcoin. So they made the first one, which was 128-bit, which was insecure. The second one, which was another 128-bit, which is also insecure. And now they've created the 160-bit, which is still secure and is the most common of this RIPE-MD, being, again, an alternative to SHA so that it's used for Bitcoin and for other alternative options. So when we're looking at our hash algorithms, it is really important to be able to recognize when you see the naming of which algorithm you're going to use, how many bits is that hash value? Yes, you really should memorize these. Now, the SHA ones are pretty easy. So SHA-2 and SHA-3 give their number of bits for their hash value length in their naming, which makes life a little easier. So do most of them, except perhaps MD5, which is 128, and the AVAL and the HMAC, which use variable lengths. The MD5 is one you want to remember. It's 128, it's not 256. And then the SHA-1, if it's brought up as a historical reference, was 160. Yes, it's important for you to memorize the different bit sizes. And remember, the RIPE-MD has the equivalent security of one lower than it. So the 256 is equivalent security of the 128, and 320 is the equivalent security of 160. More details of these are in your study guide, so this is just kind of an overview, and I do recommend you take some time to try to get these memorized. So, why do we care about hashing? Hashing introduces us to digital signatures. Digital signatures handle the non-repudiation issue. Digital signatures, or digitally signed messages, assure the recipient that the message is the one that the user sent. So I send a message to Bob. Bob wants to know, is the message Bob received the same one that I sent? Yes, it is, because I have digitally signed it. Now, there are two ways that we can do digital signatures. It also assures that the message was not altered in transit, which is a second option of the digital signature. So starting with the blue section, Alice wants to send a message to Bob. Okay. Alice generates a hash of the message. So I'm going to write my message, meet me at noon, whatever it happens to be. I'm going to generate a hash, so my message digest of that. I am then going to encrypt my message digest with my private key. If I'm Alice, I use Alice's private key, my key that only I did. This is creating the non-repudiation. Yes, I sent it, because the only way that Alice's private key would be if Alice did it herself. Then she appends the signed message digest, it's the one with my private key, the one that's encrypted, into the plain text message and sends the message to Bob. Bob is able to get the message digest, which was signed, and decrypts it with Alice's public key, which is available publicly. He decrypts it, and then he uses the same hash function on the message that Alice did to make sure that they return the same value. As long as the message digest that Bob created with the same hash value is equal to exactly the message digest that he decrypted from Alice's public key, compare the two, and you should be good. We can add one more layer to this. That's the brown area here, which is Alice can encrypt the message with Bob's public key. So before she sends the message to Bob, so 1, 2, 3 steps in, she appends the signed message digest to the plaintext. Then she takes the message digest and the plaintext together and encrypts it with Bob's public key. Then she sends that to Bob, which he decrypts with his private key, which he can only do with his private key, to be able to get both the message and the signed message digest, decrypts the message digest, compares them, and we can have both Nothing was changed in transit, and definitely Alice sent it because Alice encrypted it with her private key. Digital signatures handle both. That authentication, yes, Alice is the one who sent it, non-repudiation. She can't say she didn't because it was encrypted with her key, and it was not changed over transit. So we have the integrity and the confidentiality of that message. It's always good to understand the standards. The hashed message authentication code, HMAC, implements a partial digital signature using a shared private key, providing integrity, but does not provide non-repudiation. Remember, if you're using a shared private key, you're using symmetric cryptography, and there's no non-repudiation with that. But it can be combined with MD5 and SHA 2 or 3 to add that non-repudiation. So once you get that digital signature in there, you can add that in to add the non-repudiation that doesn't come by default with a symmetric key. The other option is the digital signature standard, DSS, which is what NIST uses and FIPS 186.4 uses. This uses the digital standard algorithm of DSA from Elgamal, RSA, or ECDSA, so the elliptical curve DSA. There is some discussion on FIPS, the upgrade from 186.4 to 186.5, which means that they will probably be removing the basic Elgamal DSA and just going with RSA and elliptical curve from now on as far as digital signature standards. Always good to keep up on these. You will want to spend a little bit of time going online, finding the NIST standards, finding the FIPS standards, and making sure that that you understand which algorithms are still being used and which aren't. The last thing you want to do is walk into a company and say, we're going to use this standard, and then somebody else tells you, oh, by the way, that's deprecated. We're not using that standard anymore. So always keep up with what the current standards are based on the NIST and the FIPS standards. Okay. At this point, we're going to start introducing public key infrastructure, the infrastructure that is in place to understand how to make these public keys so that people can share them and it is all controlled at some level. So, understanding a certificate. Certificate is the piece of information that assures people that they're talking to the right person. Somebody has validated that you are you. In a certificate, we're following the standard of X509. So if you ever see X509, know that that's referring to certificate standards in PKI. And inside that standard, we say that we're going to create a serial number, the identifier, the issuer's name, the validity period, how long it is valid, who's the subject, and what's the subject's public key. Not their private key, their public key. Remember, asymmetric uses a public key. The list over to the left, the right, is going to be a list of different certificate authorities. They are reputable companies who verify the issuance of a certificate. Now, some of these you may recognize, some of them you may not. The point of this is that literally anybody could be a CA or a certificate authority, but it's all based on their reputation. So do you trust Symantec? Do you trust AWS? Do you trust GoDaddy or DigiCert? Who is the company that you are going to trust to issue your certificate? They become the certificate authority. A registration authority works with the certificate authority to verify your identity, whether that means that you provide them with a driver's license, or you provide them a social security number, or you provide them with some piece of identity. This is my taxpayer identifying number so that you know that I'm the company I say I'm going to be. However you are going to verify the identity, I am going to verify that I am me. I'm going to go through a registration authority to verify my identity and give that information to the certificate authority, who is then going to say, yes, Cheryl Simpson did this, John Doe did that, Microsoft did this, and they are the one who has issued this certificate. Remember, the certificate creates or identifies your public key. It also has a validity period. With a certificate, first thing you do is you go through enrollment. Then you get your verification and you get your certificate. At some point in the future, that certificate may be revoked. It may be revoked for a lot of different reasons. You no longer want to use that certificate. Something has been compromised. For whatever reason, the company doesn't exist anymore. The person doesn't exist anymore. We're going to revoke that certificate. When you create a certificate, you generally will give it a validity period. This is good for 1 year. This is good for 5 years. This is good for 2 years. This has actually become a significant problem with the changeover from TLS because the validity periods have been decremented to about a year, which means you need to create a new certificate every year to make sure that you keep your certificates up to date. With a revoking certificate, we can choose to have a revocation list, so you can verify against a list. Is the certificate in the list of revoked certificates? There's also an online certificate status protocol, which will allow you to check through there, and the concept of certification stapling, or identifying different certificates as they have been revoked. Remember, a revocation of a certificate can happen because the time period has ended and or it is actively revoked for some reason. This certificate is no longer good. It's important for you to be able to recognize the standard and the extension that goes with it. Now, the Distinguished Encoding Rules, or DER, uses a binary as opposed to the PEM, or Privacy Enhanced Mail, which uses a text-based. It's important to recognize that the file extension of a CRT is used in both of those standards, so you can't know just from the extension which standard you're using. It is important to recognize which standard you are using when you create your certificate so that you know how to verify that certificate. So these are all things that you want to understand while you are getting that certificate. With your asymmetric key management, it is very important that you pick your encryption system wisely. Remember, we don't want to do that security through obscurity. If everything else except the key is known, it shouldn't be a problem. It's okay that everything else is known. So select your keys wisely. Make sure your key length balances your requirements. Keys should always be random. They should always be secret. When they need to be replaced, they need to be retired, so keys are no longer valid. Key rotation, and you need to have some backup keys just in case something happens and we have a backup option. Some companies choose to use a hardware security module, which is used to store and manage keys. It also can increase hardware acceleration for increased efficiency. Both Microsoft, Amazon, with their cloud computing, offer key management systems through an IaaS. So a as a service, infrastructure as a service, using key management so that that can be handled on the cloud. Remember, if you have it all in one location, that makes it available if something were to happen to your local server. However, it is now in one location, and if something were to happen in that location, you're in trouble. You don't want to lose your key. Losing your key would be bad. So keeping your keys wisely to any encryption kit system is really an important part of it. So now we're going to start talking about hybrid cryptography. Again, the concept of using both asymmetric and symmetric cryptography at the same time. TLS being the most common version of this. The way we do this is we set up our initial connection using an asymmetric cryptography. The asymmetric, all it is supposed to do is pass that key. We just need to pass that symmetric key back and forth. But we're going to do it asymmetrically so that we can get the key, because the key distribution is the hardest part of symmetric cryptography, being able to do that key distribution. So we're going to use asymmetric, which is good for small messages, to be able to send that key across. Once we have the key, then we set up a connection with symmetric for data transfer so we can pass the data path easier with the symmetric key. And then we use the private keys to encrypt the message, again, using symmetric that way. So being able to do hybrid cryptography like TLS uses both symmetric and asymmetric cryptography. The asymmetric to pass the symmetric ephemeral one-time key, and then the symmetric to actually encrypt the tunnel to allow the data transfer to go through in that way. A couple of ways in which cryptography is used, so applied or applications of cryptography. Obviously, portable devices. Now, a portable device these days can be anything from your cell phone to your laptop, anything that could be lost or stolen. We can have some cryptography installed with maybe a TPM, Trusted Platform Module, which is a chip on your motherboard that's used for key management. We can have lockout devices. We can have the ability to say, lock my phone, wipe my phone if it's stolen. We can do the same thing with a computer. For email, we want to have that confidentiality, integrity, authentication, and non-repudiation. So we can use applied cryptography to be able to encrypt our email and be able to add that digital signature to add the non-repudiation part to it. Pretty Good Privacy, or PGP, was Phil Zimmerman's way of handling email, which combines a certificate authority to create a acceptable web of users. These are people that the certificate authority has already verified to add pretty good privacy. It wasn't as effective as the best in cryptography, but it's good enough for most situations. And then, of course, our SMIME, or our Secure Multipurpose Internet Mail Extension, which uses RSA and the X509 certificates. It's the kind that's used in Outlook or Apple or G Suite's mail programs. SMIME is designed to be able to make a secure mail extension so that information can't be passed in plain text. Most of your web applications are going to have some layer of security, HTTPS. The S part of it implies that this has some layers of security. So basic web applications generally use some version of SSL and TLS. Remember, TLS actually uses SSL as it was created by Netscape to provide some client-server encryption when we do HTTPS. Using SSL in TLS and digital certificates, we are creating a hybrid cryptography. Remember with TLS 1.0 and 1.1 are both deprecated. Don't use them anymore. If you are, you will get that really fun warning that says this website is not acceptable. TLS 2.0 or 1.2 is the current standard, and 1.3 is much more secure and adds some performance improvements. So if you can build it into TLS 1.3, that is recommended. When we use a TLS suite, we generally describe all the different parts of the TLS encryption environment, starting with what is the key exchange, what is the authentication, what is the encryption algorithm, and what is the hashing algorithm. The example given here is a TLS with DiffieHellman with RSA and AES using 256-bit, which uses CBC with a SHA-384 hashing algorithm. Keeping track of all of the different things that could be different in your TLS application is how this big long line works. Again, you need to recognize DH means DiffieHellman, RSA is RSA, AES, encryption standard at 256 bits, SHA-384 bit is the SHA-384 bit algorithm, so on and so forth, and blockchaining. So the different things that go in with your TLS suite. So when you see this big long line, you understand what all this information means. A couple of examples of this is the Tor browser. So the Tor browser, which is the Onion router, TOR, is a way to get onto the dark web. No, we do not describe the dark web in this class. I'm not going to talk about it other than bringing up that Tor was designed as an anonymous routing traffic through encryption. We called it perfect forward secrecy. Essentially, you're going through multiple traffics and you can't get back. So they can't find out where you were from. It's a way of anonymizing yourself on the internet. There's some discussion on how secure it really is and who is actually controlling it, and I'm not going to get into that. Another option that we have for using cryptography in web applications is steganography. Steganography is simply the idea of embedding a secret message within another message, more often than not an image. The example here with iSteg is being able to take, here is my image picture of my kids playing at the park, and I'm going to embed in that my secret message of meet me at noon to pass me the money, whatever it happens to be. You can use the ability to use lower bits in some pictures to be able to embed your secret messages, steganography. We can also use digital watermarks to protect intellectual property by using steganography to be able to say, this is mine. When it is stolen, when somebody else uses it, you can always pull that message back out and say, see, it's exactly the one that was stolen. Here's my watermark. So digital watermarks are used to protect intellectual property. Another application of cryptography in networking is going to be either our IPsec or our circuit encryption. So circuit encryption uses linked encryption and end-to-end encryption to make SSL. So, or SSH, secure shell. So link encryption means that we are going to create a secure tunnel between 2 points. It can be done either with software or hardware. And the point is to encrypt all of the data, the header, the address, and the data itself. End-to-end encryption, which is what TLS does, only encrypts the data. It does not encrypt the header. The point of this is not to say I'm going to hide who I am. This is just going to say I'm going to hide the message. So the data is encrypted in end-to-end. Link encryption is a tunnel which encrypts everything. Secure shell uses end-to-end, but it protects against man-in-the-middle or eavesdropping or IP and DNS spoofing by encrypting the data through that tunnel. IPsec, or Internet Protocol Security, is the standard that's used by the Internet Engineering Task Force. IPsec consists of an authentication header and an encapsulating security payload, AH and ESP. Both of these are explained further, so I'm not going to spend a lot of energy explaining them now, but they do use two modes. One is a transport mode, which is your end-to-end. I'm just transporting the data. And the second is link, which is your tunnel mode, being able to do all of your data, your header, your address, and your data all in a tunnel. So you do want to remember with your IPsec, you have your authentication header and your encapsulating security payload, and we have two different modes. The tunnel mode, which is all data, and the transport mode, which is just the data, but the header and the address information is available in plain text. A couple of emerging applications are things like blockchain. Blockchain obviously has become a pretty common conversation with cryptocurrency and Bitcoins. The point of a blockchain is simply having a distributed, immutable, public ledger. So distributed, it's stored in multiple locations. Immutable, it cannot be changed. Public, meaning everybody can reference it. And ledger is a list of transactions between two items. That's it. It isn't always cryptocurrency. It can have lots of other uses. The point is to store the records in multiple locations, not being able to change them, immutable, and that it's available to everybody. It's open, it's transparent. It was originally designed with no central authority, although there is conversations once you get into Bitcoin and different cryptocurrencies on who the centralized authority is in those situations. Lightweight cryptography is specialization in hardware designed to limit power consumption or low latency. Things are running so fast, high velocity of data, that we want this the fastest we can go, and we're all about low latency, or perhaps high resiliency. Is the preservation of the data the most important? And it's okay if we had to get between having no data and having available data. We'd rather have available data than no data, because the preservation of the data itself is the most important thing, rather than the confidentiality or the availability. The preservation of the data is the most important part. High resiliency. Homomorphic is a specialized case of encryption that is designed to protect the privacy of individuals, PII, but wanting to aggregate or calculate based on that data. If I had a collection of data and I wanted to pull out all of the PII, but I still wanted to find out how many people in the group were over the age of 65. If I don't have the PII, how do I get that? Homomorphic encryption will allow you to get the same calculation aggregate out of the data without making the data public. So it's designed to protect the privacy or PII of your data and still get the aggregations or calculations that you wanted from that data without releasing it. And our last slide with this chapter is going to be our cryptographic attacks. So it is important for you to memorize the different types of attacks that you can have here. Based on cryptography, they are all cryptographic attacks. So attacks that are either attacking the cryptography, attacking the ability to do crypto analysis on your data. So different versions of these. The first is ciphertext only. You have the ciphertext and that's all you have. A way to solve that, frequency analysis. If I can figure out that you were doing a substitution cipher or anything like that to be able to do frequency analysis, how many E's, how many words that are 2 letters or 1 letter, can I figure out some frequency analysis to figure out how to solve a ciphertext only attack. The known plaintext is where the attacker has both the plaintext and the ciphertext, and he can use those to determine your algorithm. So I know the plaintext and I know the ciphertext of this message. So I can figure out what was the algorithm you used. So the next time I get your ciphertext, I can figure out what your plaintext was because I know what the algorithm is. So that's a known plaintext. You know the plaintext and the ciphertext. Chosen plaintext is where the attacker has some of the plain text and ciphertext, but not all of it. Maybe it's a footer or a salutation or something on there that the attacker has some of the plain text and some of the ciphertext. This is how we solved things where we could find out that the last 2 words in every message from the Nazis was Heil Hitler. By doing that, we could use some analysis to know what the plain text was going to be at the end of every ciphertext and use that to do analysis. A chosen ciphertext is where the attacker can decrypt some of the ciphertext to determine the key. Again, you don't have all of the ciphertext, but you have some of it. And sometimes some is enough to be able to determine the key or some other algorithm that is being used. Meet in the middle is where the attacker knows the plain text and encrypts it over every possible key to try to figure out what the key is. It's kind of a brute force attack, as opposed to the man in the middle, which sounds very similar, which is where the attacker actually sits between the sender and the recipient and then gets the information from the sender and then modifies it and sends it off to the recipient and then is able to switch it back and forth. Obviously, if you have the attacker in the middle and you're doing the DiffieHellman Key Exchange, the attacker in the middle gets to be both sides and be able to figure out what the algorithm is going to be. Birthday attack takes advantage of collisions. Birthday attack follows the logic of if you put 100 people in the room, there's like a 50% chance that 2 of them will have the same birthday because of number theory, and there's only 365 possible birthdays. So birthday attacks handle collisions. They are all about collisions, and they use reverse hashes to be able to handle, if they can figure out what the collision is going to be, they can do a reverse hash, perhaps substitute a different hash by using that birthday attack. So if I can find a way to create the same hash that you have from a different subset of data, I can make that subset of data do what I want, and then you don't know the difference because the hash is matched. And then, of course, a replay attack where the attacker uses the previous session to open a new session. We already had a key. We are going to try to use the key again tomorrow, and I know the key because I figured out the key. So I'm using my previous session to find the key and then open a new session with you because you think I'm the same person. Some of these attacks are analytic. Some of them are based on your implementation. Some are statistical. Some are just basic brute force. Some are fault injection. Some are side channels. And some are all based on timing. Sessions are all based on timing. So different cryptographic attacks that can attack based on the cryptography algorithm, the hashing, what way you are choosing to do your cryptography. So in summary, from Chapter 7, it is important for you to understand the key types in asymmetric cryptography, the 3 major crypto systems, so your RSA, your DiffieHellman, and your elliptical curve. Understand how hashing algorithms work. How do you use salts to increase the security of hashing by adding randomness? Understanding how digital signatures and digital certificates are created and verified using the public key infrastructure of certificate authorities. So digital certificates through certificate authorities, understanding your web applications using your TLS and your SSL, your SMIME, and your PGP, being able to describe IPsec with your authentication header and your ESP, and explaining some of your common cryptographic attacks. Thank you for watching this lesson on CISSP Chapter 7. Please come back next time. Have a great day.